And you're back. Let's keep doing examples. So can we do the same sequence of steps to graph this rational function? Okay, so there is a nice list, like in the book, a little table, like step 1, step 2, do this. So hopefully you're referring to that. So step 1 is factor everything. The numerator factors difference of two squares. The denominator is just an x. It's already factored. So then we ask, what's the domain? Everything but 0. It is in lowest terms. There's no cancellation to do, which means we can go right to finding intercepts. So x can't equal 0. I can't plug in x equals 0, which means there is no y-intercept. There are two x-intercepts, because the numerator can be 0 if x equals -2 or if x equals 2. They each have multiplicity 1, which means that they're odd multiplicity roots. The graph will cross. So the two roots involve crossings. The denominator only had a single 0, and it was already in lowest terms, so that gives me a vertical asymptote. X equals 0 is a vertical asymptote. It's of odd multiplicity, which means that the asymptote does opposite things on both sides. It goes to +infinity on one side and -infinity on the other. I don't know which way yet, but it does switch. Step 5, the numerator is one larger degree than the denominator, which means I need to find a slant asymptote. So I'm going to do the polynomial division. It's pretty straightforward because the degrees are quite small. Okay, so this quotient is just x. So our original function, by the way, was just, where's my pen go? Here it is. It was x squared minus 1 over x, and this division has told us the result is x with a remainder of -1 over the original denominator. Let me write that clearer. X minus 1 over x. So as x gets really big, this bit goes to 0, and fundamentally we look like the line y equals x. We have a slant asymptote. Okay, so use a dashed line for vertical and horizontal and slashed asymptotes. So we would go ahead and graph that as a dashed line. Then whenever you have a horizontal or a slant asymptote, ask, do I intercept it? So does my original function, which remember was x squared minus 1 over x, ever equal the slant asymptote of x? So I set them equal to each other, multiply that x, and notice we get a -4 equals 0, which never happens. -4 is never equal to 0, which means there are no intersections. So when I draw this slant asymptote, I know the graph is never going to cross it, because these two things could never equal each other. Okay, so now we split up the domain, the real number line, into a bunch of intervals using zeros of the numerator and zeros of the denominator. So we get 4 intervals, up to -2, from -2 to 0, from 0 to 2, and from 2 to infinity. Okay, and the way I typically do this is actually by drawing it. Here's the number line. Then I say -2, 2, 0. So I have 4 intervals. This one, this one, this one, and this one, which are written out in interval notation here. On these intervals, the graph will be positive or the graph will be negative. You can then take test values somewhere in between to determine which is which. So on that left interval, we got negative, then we got positive, then we got negative, then we got positive. It doesn't always flip-flop back and forth, okay? Because sometimes graphs can do things like this, where you have a root, but you're positive on both sides, or you could have a vertical asymptote and be positive on both sides, or negative on both sides. You actually have to check. Every once in a while, someone goes through and sees 2 examples in a row where it keeps flipping, positive, negative, and they think that's always what's going to happen. Nope, you've actually got to check every interval. So now we take our vertical asymptote and our slant asymptote, and we know graphs never cross vertical asymptotes, and we know this one doesn't cross its slant asymptote either. We take our test values that we computed in the previous chart and we put them down. We've got the information, we may as well use it. And now we just sort of go, where is it positive and where is it negative? Well, from -infinity to -2, I know the graph is going to be negative. From 2 to 0, it's going to be positive. This is just from the previous slide. From 0 to 2, it's going to be negative, and from 2 onward, it's going to be positive. Combine that with the vertical asymptote, and here I'm positive, so I have to do something like that. It's of odd multiplicity, so I have to come in from the other side, which matches the fact that the graph is negative here. Then I go through this root. It's an odd multiplicity root, so I actually cross to become positive. Then I'm positive and I'm going to approach the slant asymptote but never touch it. And on the left-hand side, I go through this root. It was a root of odd multiplicity, so I cross. I go through this point because we computed it. Then I approach the slant asymptote, but I never actually touch it. So there's the graph, which is given to us fairly nicely here. But really, it's all that same argument. Okay, let's do another. Graph the following rational function. Do all the same steps. So genuinely pause here, try to follow those same 6 or 7 step process and see what you get. Take a few minutes and then unpause the video. Okay, so there is no factoring to be done. The reason you know that, now the denominator is already factored, it's x times x. The numerator, you would try to factor by finding roots. So you would set the numerator equal to 0, which you would then get this. But this is an even power of x. It's never going to be negative. So there are no roots. Okay, so there are no roots of the numerator or the denominator. This is already completely factored. Write it in lowest terms. It already is. There was no factoring to cancel out. The domain is everything other than 0, because that would make the denominator 0, which means there's no y-intercept. But we already know, in fact, that the numerator has no roots either. That was also part of our seeing that it was completely factored, which means there are no x-intercepts either. There are no intercepts at all. It's already written in lowest terms, so root of the denominator is a vertical asymptote. But now, compared to previous examples, the denominator, the root 0 had the term x squared associated to it. That's of even multiplicity. That means the asymptote will be positive on both sides or negative on both sides. I'm still not sure which, but it's the same on both sides because it was an even multiplicity vertical asymptote. Now, since the degree of the numerator is 2 larger than the denominator, there is no slant or horizontal asymptote defined. We can kind of round this off to say, more or less, this is going to look like x squared. Okay. You can verify it doesn't actually equal x squared. If you tried to set your function equals x squared, multiply both sides by x squared, you'll get x to the 4th plus 4 is equal to x to the 4th. In other words, 4 equals 0. No, it doesn't. That's never true. So this graph does not intersect that parabola. So if I put that parabola of x squared using dashes, I know the graph should never cross it. But it will get fairly close to it. Okay, we've got no roots of the numerator and a single root of the denominator. So we only have to divide the number line at 0 at the root of the denominator. Therefore, I have 2 intervals up to 0 and past 0. We take some test values. 1 and net minus 1 are a pretty good choice. And we get positive on both sides, which we knew would happen. They'd either both be positive or both be negative, because we know the asymptote, the vertical asymptote, was of even multiplicity, so it would be either positive on both sides or negative on both sides. And there are no roots, so I don't have to worry about crossing. So one test value gives me all the information I need. So we expected them to be the same, and they're both positive. And here's how it looks. So why is this? We know that this dashed parabola, the function is never allowed to cross it. But we know we have this vertical asymptote going to positive infinity here. I know it's positive because we know these test values were positive. So the graph has to come down from the vertical asymptote and hit this value. But then as x keeps going to the left, I'm just not allowed to cross the parabola, but I am supposed to get close to it. So really there's no other option. Similarly on the right, I have to come hit the test value. I have to keep going, and I have to get close to the parabola without ever crossing it. So there it is. That's what the graph looks like. I'll clear it out because their picture's better than mine. Okay, so again, we'll take a break here. Come on back for the next video.